All right, let's move on to BJT's part 2. One of the things I want to note right off the bat is everything we've done so far is for a PNP BJT. Now we also know, or at least those that have taken electronics or seen a little bit of them, know that there's something called an NPN BJT, where all the dopings are reversed. And so do we need to go back through everything for that? The answer is no. All that happens is that the currents are all reversed, and so your band diagrams will be reversed. So instead of dipping down, it'll be NPN, so it'll go like this for the conduction band. And the other thing that changes is instead of injecting holes this way, you'll be injecting electrons, and electrons have a negative charge, and so the currents are in the opposite direction. So basically everything we talked about just flips, okay? Now, as we go into today, I want to remind you why we care about BJTs. They are great for high power, high frequency amplification. We'll start to look at some spec sheets today with this sub-lecture that show you some of the performance specs for them. And the key thing is that a small change in base current leads to a large change in collector current. So we said last time that small base current, large emitter to collector current, that's our amplification. So if we want to understand amplification, let's look at an idealized simple model that assumes several things to begin with. For this model, we're going to assume there's no reverse saturation current here. It's so small, the I naught's so small, that we're not going to worry about that in our model. We'll assume DC or low frequency, so we won't be at the point where we're at the frequency limit for this device. And we're going to neglect recombination in the depletion regions, which is a reasonable estimate for typical diodes, but we will not neglect recombination in the base because that's important. As holes come across, some of them will recombine with electrons, and that's a big factor that gives us our base current. Okay, so now I've introduced some new current labelings here, and I want you to notice the directions first. Here's IE, it's lowercase IE, okay? In this direction, positive charges moving this way means current in this direction. And then I can break this up into two components here, IEP and IEN. IEP are holes moving this way, right? That's the holes moving this way, positive charge this way, current in this direction. IEN is in this direction too. It's electrons this way, right? Well, electrons have negative charge, and so in terms of current flow, electron current would be in this direction. I also have IB. I know I'm bringing electrons in, but they're negatively charged, so that's the same as current flow out. And lastly, I have IC here, positive carriers moving in this direction. There's my collector current. So what I want to do next is I want to relate IEP, the holes here that are injected across here, to collector current. And I'm going to relate them using a proportionality constant, B, this is not beta, this is B, called the base transport factor. Basically what this says is how many holes do I get out to the collector compared to how many holes I started at the emitter. How efficiently do they transport across the base? This is an efficiency of transporting electrons across the base to the collector. Transporting the holes, sorry. Here comes the holes, okay? I'm transporting them across the base, and if I have a very high efficiency, which is what I want, most of the holes will make it across to the collector. Okay, so this gives me how many holes that are emitted turn into how many holes that are collected. Now, if I make a BJT that's well designed, I will also want pretty much just hole injection, not electron injection across the emitter base. So I want tons of holes to be forward bias diffused, but not many electrons. And we're able to do that because we make this P plus N, right? There are not many electrons to go this way, tons of holes to go this way. And so if I want to measure that, I'm going to measure that using something called emitter injection efficiency, which measures the following. Emitter injection efficiency, which is how efficient are you at injecting holes versus electrons that I don't want to inject this way, is calculated as, well, how many holes are injected across, IEP, divided by the total current. So how many holes are injected across plus the electrons that are injected this way. So ideally, right, I would like no electrons coming this way, because the smaller this current is, the smaller my base current, the larger my amplification of base current into collector and emitter current, right? And so if I want this current component to be small, then you could see this term could get closer and closer to unity, which would be 100% efficiency. Okay? We can further define another term, which is current transfer ratio, which says total emitter current and total collector current, how do they relate? Okay? And so current transfer ratio is how much collector current out one side versus emitter current in the other. I know that as emitter current comes in, I lose some of it to recombination, and so I'm left with less collector current out this end, right? Because I have more holes coming this way, I have some electrons going this way, which increases IE compared to IC, which is just holes that get across. And so ideally, if I design this well, most of the holes will get across. If most of the holes get across, IE and IC become very close, and I get a close to unity for my current transfer ratio. Remember, we know that IC right here, right? IC is base transport factor times the emitter hole current, right? And so I could substitute that in there. I know my emitter current is just IEP plus IEN, right? Emitter current is just IEN plus IEP. Holes this way, electrons this way. Okay, so I can put that there. And then I'll recognize that this whole term right here, IEP over IEN plus IEP, that's just emitter injection efficiency, so I end up with B, base transport factor, times emitter injection efficiency is equal to current transfer ratio. So now you can see how I'm starting to form these terms that measure performance for a BJT and figure out ways where I can relate them. Again, in an ideal world, what would the values be for B, gamma, and for alpha, current transfer ratio? I would like them all to be as close as possible to unity, okay? If I have good design, and if I have good design and I'm going to get these close to unity, well, I want the base to be lightly doped compared to the emitter, right? So I don't have recombination here of holes as they go across, and I'd like my base width to be as lightly as possible, again, so I don't have much recombination. And I like this to be lightly doped here in the base because that means there's less electrons diffusing this way. Do all this, and these terms get close to unity. Now, we said we would like our current transfer ratio to be close to unity, but this says nothing about gain. And so we want to basically figure out, what is our gain in terms of IB turning into IE and IC, okay? And so we've got all these terms, and let's turn our attention to IB and figure out what components make it up. So my base current, IB here, has a couple components. One, it has IEN, right? Electrons going this way, there's IEN, and that's current in this direction. And it also has this term here, which is holes that don't make it across. Well, this is easy to calculate, okay? If the holes that make it across are IEP here times base transport factor, then the holes that don't make it across would be IEP times 1 minus the base transport factor. Think about it this way. Let's say my base transport factor is 0.99. That would mean for every 100 holes, 99 show up here, right? Well, if I have 100 coming in and 99 coming out here, then I know by conservation of these charges, that means I've got 1 here, right? Well, lo and behold, the number of electrons I need to be coming in is 1 also, right? And so if I do the equation here, right here, I've got 1 minus 0.99, right? Which would give me 0.01. And if I multiply that by the 100 coming in, which would be IEP times 100, that would give me 1, and that's how many I needed to recombine there. Okay? And so now you can see how I can basically calculate my total base current from those diffusing across to the other side and those that are recombining with holes that are trying to diffuse across the base junction as well. Again, right away we notice that neither of these components helps us to increase IC, so as usual, we want these components to be as small as possible. We want the amount diffusing here to be as small as possible, and we don't want much recombination of electrons and holes in the base either. Okay, so here's what we know so far. We've now got terms for current transfer ratio, we've got base transport factor, emitter injection efficiency, and now I've got a terminology for the base. So for maximum amplification for a BJT, we desire to have a large change in collector current to a small change in base current. Okay? And so how are we going to calculate this? Again, I want a small base current, very few electrons come in here, to give me a huge change in the number of holes going this way. Well, it's quite easy if you think about it. Next slide here. So how we can basically calculate our amplification factor is, well, if we want a large collector current for a small base current, so tiny base current comes in here of electrons, and you get a huge amount of collector current out, I'll just look at the ratio. The ratio of collector current to base current will give me my amplification factor. And so I'm going to start to substitute in here some terms. We already have IC equals base transport factor times IEP. I put that in right here. I've got my currents for base current. We did that on the previous slide, right? There's my currents for the base current, the two components. And then what I'm going to do is I'm going to take both the terms in the numerator and the denominator, and I'm going to divide them all by IEN plus IEP. So I'm dividing all the terms in here by IEN plus IEP. If I do that, and I notice that this term over here, I have 1 times this, then I'll have this plus this, and I'll have IEN plus IEP over IEN plus IEP. Well, that's just equal to unity, right? So that's easy. So I end up with a 1 for all this stuff. And then I'll recognize that this term here and this term here is just emitter injection efficiency. And then I can calculate then my amplification factor as IC over IB is equal to base transport factor, emitter injection efficiency, 1 minus base transport factor times emitter injection efficiency. This is this simplified down with the substitutions I just talked about. And I know that my base transport factor times emitter injection efficiency is also equal to current transfer ratio. We showed that in the previous slide, so I can simplify it down. And again, this is all equal to amplification factor beta. Okay? And so beta is basically, if I have a large amplification factor, then I will have a huge change in collector current for a small change in base current. So, if I want to have an amplification factor of 100, let's say, for example, then base current might be, 1 milliamp. Collector current would be 100 milliamps as I bring in 1 milliamp, and my amplification factor in that case would be 100 for this BJT. Okay? And again, if we design this well, our current transfer ratio can be close to 1, right? If it's like 0.99 or 0.995, then you could see that this becomes very large because you end up with 1 over 1 minus something close to 1, small number here, which makes this ratio become very large. And so you can get very large amplification factors for the BJT if you design it well for all these terms. So, at this point, make sure these make sense. Look at all these terms and where the currents are comprised of for all these things, and make sure they make sense, because they're a great way for us to calculate the performance of the BJT. And in a lecture or two, we'll start to basically feed in doping levels, widths, dimensions, things like that, to start to be able to calculate all these terms as well. So, now I want to look at amplification one other way as well. And how we're going to do this is we're going to assume unity in emitter injection efficiency. Basically, neglect electrons coming this way, assume it's almost all holes. And that's a pretty fair assumption because this is so heavily doped compared to this side that the amount of electrons coming this way is just minuscule. You really don't have to worry about it if you design the BJT well. And so I'll assume that the only component left for the base current are those electrons which have to recombine with holes that don't make it across the base. So, if I start doing this assumption, okay, we know that we must always have charge neutrality in the base or any type of semiconductor. Charge neutrality means that if I have some area of semiconductor and I add one positive charge, then I got to have a negative charge. If I add another positive charge here, somewhere I've got to have a negative, and they all have to balance out. Same number of positive and negatives in the semiconductor in general. Okay? Now, let's ask this then. So, if I don't have electrons going this way, because basically most of them are just sitting here to recombine, okay? This is super small, I neglect it. So they just sit in here until they recombine with holes. Then I put electrons here, they just sit there. And you can kind of see that here too. The electrons are just sitting here. They're like the water, right? So they're sitting down here in this little bucket, waiting to basically match up with a hole that doesn't make it across and recombines with them. So, based on charge neutrality, if I added 5 electrons to the base, at any given time, how many holes would there be? So if I added, there's 1, 2, 3, 4, 5. At any given time, how many holes do I have to have in the base as well? Well, we know that by charge neutrality, I have to have 5. And so I have 1, 2, 3, 4, 5 holes, okay, at any given time. Now, let's look at this in a dynamic sense in terms of what's happening versus time. So the electrons we added, do they just sit there? Well, the answer is no. We know they don't just sit there because over time they're going to recombine, right? And so the answer is how long until they disappear? Well, they're going to disappear within their lifetime. Remember, we've got carrier lifetime. So they will sit there until they recombine, which is roughly tau n, their lifetime in the base. Now, during the time it took for these electrons to recombine, what were the holes doing? Were these holes just sitting here? Ask yourself that question. Are these holes just sitting here? Well, the answer is no. We know that at that time, the holes are zipping across here at very high speed. Okay? And so how much time does a hole spend in the base? Is it longer or shorter than the time for an electron? Well, the time that the holes spend in here is much shorter. Okay? And so these holes are just zipping across there. And so they're going to have something called a transit time to get across the base, and that'll be shorter. And so the question is, how can we use this to calculate amplification factor? Well, what we're going to find is we can take the ratio of these two time coefficients and get amplification factor. And that makes sense too because there's no units for amplification factor. It's just a number, right? And so if I take the ratio of two things that have the same units, then it'll be unitless as well. Okay? So, let's do that basically. Okay? I want to calculate my amplification factor. And so that will be basically the rate at which electrons are recombining. But here's a key substitution I'm going to do. Okay? Remember that the electron and hole lifetimes are equal. Okay? So when an electron recombines, a hole recombines as well. And so the tau for an electron is equal to the tau for a hole. So I'll substitute in the tau for a hole divided by the transit time, and that ratio will basically give me my amplification factor. And we built this up based on having charge neutrality in the base. Okay? And so my collector current over my base current, which gives me amplification factor, can also be calculated by the whole lifetime divided by the whole transit time. If I want large amplification, ideally, what would I want? Well, I would want the whole lifetime to be large, right? A large whole lifetime in the base means that the holes don't recombine, right? If they have a long lifetime, they're not recombining very fast. Well, if they're not recombining very fast, then that means my base current is going to be small, which is what I want for a large amplification factor. And so the other factor is the transit time, and so the faster they make it across there, the more showing up on the other side. I take the ratio of these two things and I get my amplification factor. So we can build upon our knowledge here and ask ourselves, what happens if we restrict or increase the flow of electrons coming in from the base contact? Well, again, and this is important, we must maintain charge neutrality. Same number of electrons and holes in the base at any given time. So any change in electrons in the base requires a much larger change in holes flowing through the base. So if I basically, if I have my bands and I add in, 10 electrons here, then that gives me on average 10 holes at any given time that are zipping through there. okay? They're flying through there. If I double the number of electrons in the base to 20, then at any given time, I have 20 moving across there. A great way to understand this is consider that the BJT is just a highway and these are cars, okay? So if I add one electron, then I could have one car, bear with me on my drawing here, moving down through the freeway, okay, on average. And let's just say I'm taking a snapshot of the base. This is my photograph. I'm taking a camera photograph here of the base here, okay, at any given time. Now, if I were to double the number of electrons I have in the base, okay, then to 2, then at any given time, I would have 2 holes or cars moving down the freeway here, okay? Now, these aren't standing still, so basically it's like being on 71 or 75. If you look at the number of cars moving at any time, if the speed is constant, which is true for the BJT, the speed they're moving across is fairly constant, then the amount of current will be the number that are sitting at any given point at any given time, or the density you have there. So if I have 10 electrons, I'd have 10 cars moving through this point at any given time. I have more holes. And so that gives you an idea how charge neutrality, adding more electrons, at any given time gives you more holes, but those holes aren't moving, they're actually moving through. And so if I have 10 electrons here and 10 holes here, let's say one moves out, another one has to come in. So on average, I always have 10, but remember, they're always moving throughout the base. So any change in electrons coming in the base requires a larger change in holes flowing through the base, since most holes go through the base without recombining. Let's look at an example circuit now and start to do some calculations. So this is what we call a common emitter configuration. The reason why it's called, in this example here, it's called common emitter, is I've got 2 circuit branches. I've got one circuit branch here, I've got one circuit branch here, and if you look at this, they are common to this node here. So you could call this basically electrical ground, meaning both circuits have one common terminal here, and it happens to be the emitter terminal, okay? And so that's why we call this common emitter. Well, let's look at how this circuit works here. They already gave us some of the parameters we need. They basically gave us our whole lifetime in the base is 10 microseconds. They gave us our transit time in the base. How long it takes holes to get across there is 0.1 microseconds. I can therefore calculate my amplification factor to be 100 for this BJT. Now, if we want to figure out our currents through this thing, let's look at the rest of the BJT. Well, the first thing I want you to notice here is that I've got voltage applied across the emitter and the collector. So I've got plus 10 volts. That makes sense because if that's positive volts, I want positive voltage here. That will forward bias the emitter base, which is what I want. But more importantly, that puts a reverse bias on the base collector. Okay? And so I have to have the collector, if it's going to collect, it needs to be reverse biased. And so this 10 volts gets dropped across the base collector because this forward bias is, and the voltage gets dropped across the reverse bias diode, which is the base collector. So everything's set up now. I've got my collector collecting because of the external voltage I put here. And so all we need now, if we have amplification factor, I know my collector is going to do the collecting. I need to know basically what's my base current. Because if I know my base current and I know my amplification factor, I can calculate my collector current. My base current's easy to calculate in this example. I've got a 5 volt supply, 50 kiloohms. 5 volts divided 50 kiloohms means I have 0.1 milliamps of electrons moving in here, right? Negative side of the voltage is this way, pushes electrons into the base. Electrons have negative charge, which is current in this direction. And if I have 0.1 milliamps of base current, amplification factor of 100, well then my collector current is 10 milliamps, 100 times the base current. So now we did a simple calculation of a BJT in a circuit. Okay, so let's wrap this up and then we'll have one last topic for BJTs. But let's make sure we can answer these questions. This is a great review. Here I have a spec sheet. And let's see if you can understand and digest this spec sheet and make sure it makes sense in terms of the things we've learned for this course. So here's our spec sheet. It's for a commercial PNP BJT. Here's the part number. It's by Toshiba, and it's an audio frequency general purpose amplifier. Okay? So the first question I have is, how do you get the amplification factor? Well, there's two ways to get the amplification factor. The first one is sort of obvious. If I look down here, I should be able to find the amplification factor somewhere. So here it is right here. It says here DC current gain. And if you set the DC current gain up with the right parameters, here's the reverse bias across the collector, you find that your current gain can be anywhere from 200 to 700. Okay? And so it's somewhere between 200 to 700 depending on how the BJT is working. Now, the other way we could get our amplification factor is we know that the amplification factor is collector current divided by base current, right? Well, if I look at this curve here, I've got a curve here of collector current versus emitter to collector voltage, and I've got all these curves, which I'll explain soon, of increasing base current. And so what you can see here is if I have no base current, zero base current, I get, no matter what voltage I put across here, I get no collector current. So this is the reverse bias across the collector that makes it collect. Okay? So once I get the collector collecting, I can get current. But I won't get current until I have some base current. So here's minus 1 microamps of base current. I'm injecting electrons into the base, and then I get a current out here. Here's minus 2 microamps of current into the base, and I trace back here, I can see here's the current coming out. And so if I took the ratio of these currents, 5 microamps, and looked over here to the collector current, which is in milliamps, I will get the same ratio for amplification factor. Now, one of the things you might be asking yourself at this point is a couple things looking at this curve. First off, why is IC so beautifully linear to IB? I mean, if you look at this thing, basically I linearly increase my base current going from 1 microamp to 10 microamps, and I see a proportional increase in collector current. Well, that's simple, right? Because I know my base current is directly amplified into collector current. This is one of the reasons why BJTs are great. They are a terrific current amplifier. You have a little bit more base current, you get a proportional increase in collector current. So it's a great linear current amplifier. And using only 2 diodes we've made back to back, we can create a perfectly linear current amplifier of base current into larger collector current. The next thing I want you to look at here is collector current versus VBE here. So look at the collector current versus VBE. Here's collector current versus VBE. What's this look like? Well, this is important to answer because if you look at this, you're like, that kind of looks like a diode, right? Well, that makes sense because that's exactly what we're doing. If we are forward biasing the emitter base and increasing the voltage across here, we should see an exponential increase in the forward bias current, just like a diode, that gets injected into the base and then shows up coming out the collector the other side. And so my collector current versus VBE has an exponential diode-like behavior. The other thing here they're showing here is there's a couple curves just for temperature. Don't worry about that. We'll talk about that in a few more lectures down the line. One of the other things you might notice here is in the collector current versus the collector emitter voltage. The collector current, as you start to add emitter and collector voltage, it goes up and then it just saturates. If you're wondering why that is, well, we'll look at it more in detail in the next lecture, but it's pretty simple to understand now. Basically, all the collector emitter does, this VCE, is put reverse bias across the base collector. So once I get to enough voltage to reverse bias it, the BJT doesn't operate more efficiently, and it just gives me constant output of collector current for a given base current. So you just basically get to reverse bias for the base collector, and then the BJT amplifies, and more reverse bias just puts more reverse bias on the base collector. But just like reverse saturation current for a diode, more reverse bias doesn't change the current. So this actually kind of looks like I naught, right? Insensitive to reverse bias voltage. The last one is, notice there's a little bit of slope here. That's early voltage. I'm not going to explain that now because that's a little bit more complicated. We'll talk about that in a lecture or two.